So now that we've learned how to take derivatives, it's time to start exploring some applications of the first derivative specifically. That's what we'll cover in Lesson 4.1. So I stole this graphic from your textbook, and this is the graph of fuel economy for a car, graphing the speed of the car versus the miles per gallon. And so you can see this is a curve that goes up and then comes down. And we use the terms increasing and decreasing to describe the behavior here, in particular to describe the behavior of a function. And we use those words on a graph as we move from left to right. So this graph is increasing at the beginning, right here, because it's going upward, and it's decreasing over here because it's moving downward from left to right. So in mathematics, we like to give formal definitions to things in terms of our language that we use. So we've got some specific definitions for what it means to be an increasing and decreasing function. And I know this graphic's a little blurry. It came from your textbook, and I didn't do a good job of copying it in, apparently. But it says here that a function f is increasing on an interval, and this is an open interval, AB, if for any two numbers x1 and x2 in that interval, the y values f of x1 and f of x2 compare as follows. The left one is always less than the right one. That's how we know it's increasing. Whenever x is on the left of, or x1 is on the left of x2. And the same notation is used to describe decreasing. The only change is that as moving from left to right, we're always greater than on that interval. So basically what that means in these pictures is as follows. Here you can see we have x1 and x2, and the f of x1 and f of x2 are here. And the f of x1 is lower than the f of x2. It's less than the f of x2. The opposite is true over here. We have x1 and x2. x1's on the left, x2's on the right. And now you can see these y values. The f of x1 is higher than the f of x2. So y1 is higher than y2. That's how we describe decreasing. In common terms, it means when a graph is moving upward, it's increasing. When a graph is moving downward, it's decreasing. We always read from left to right. So now that we've described and defined increasing and decreasing, let's put this in terms of the derivatives that we've learned how to find. Here it says, recall that the first derivative tells us, that should say tells us. That's a typo, I apologize. Look at that, on the fly correction, it doesn't look any better. The first derivative tells us the slope of a tangent line to a curve at a particular point. And you'll notice that when a function is increasing, like this guy over here, its tangent is also increasing. It goes upward from left to right. And when a function is decreasing, the tangent line is also decreasing. It moves down from left to right. This line over here on the left has a positive slope. This line over here has a negative slope. And so that's what we really want to focus on. The sine of the slope of the tangent line is positive over here. The sine of the slope of the tangent line is negative over here. And so that leads us to our first theorem. As opposed to a definition, this is a theorem that's been proven. And it says three important facts about the first derivative of a function. If the first derivative, f prime of x, is greater than 0, meaning it's positive, for every value x in an interval ab, then the function is said to be increasing. So a positive derivative gives us an increasing function if that derivative is positive for every point in the interval. Similarly, when the first derivative is negative, right, when it's less than 0, then that function is decreasing, as long as it's negative for every point on the interval. And then finally, when the first derivative equals 0, right, when the slope is 0, we have a horizontal line. That function is constant for all the points in that interval. It's constant on that interval. So theorem 1 is going to be a great tool for us, because if we can find intervals where the derivative is positive, we know that function's increasing. If we can find intervals where the first derivative is negative, then we know that it's decreasing on that interval. And finally, if we can find intervals where the first derivative is 0, then we know that function's constant on that interval. So now that we've talked a little bit about these definitions in the theorem 1, let's do a problem here. They want us to find intervals where the function y equals x squared is increasing and the interval where it is decreasing. I think I left the word interval out of the first thing, but we're going to find the two intervals. So the cool thing about y equals x squared is we already know what it is. It's a parabola. If you take the derivative, you get 2x. And it's easy to pinpoint where 2x is going to be negative. 2x will be negative whenever x is negative, meaning where x is less than 0. So for every negative number, my derivative is going to be negative. What that tells me is that that function is decreasing on the interval of the negative numbers. I spelled decreasing wrong there. And that interval would be negative infinity all the way up to 0. Not including 0, though. Y prime is positive whenever I put a positive number in there. So when x is greater than 0, I'll be increasing. Oh my goodness, I am having a terrible time with the old pen tonight. But I've got my groove going here, so I don't want to mess things up and start over. I apologize. We're increasing on greater than 0 if we're using interval notation. That's 0 to infinity. And then at the single point 0, that's when our derivative is 0. And the function would be constant there, except it's only one point. It's not an interval. So we're increasing from negative infinity to 0, all of the negative numbers. We're decreasing, and we're increasing on the positive numbers, 0 to infinity. I think a graph will really tie this together since I'm stumbling over my words. So let's check out the picture. Here's the graph of y equals x squared. It's the familiar parabola that you're used to. And notice we were right. The function is decreasing for all the negative numbers, right? For all these negative values, that function is decreasing. The function is increasing over here for all the positive values of x. And so that's where the interval notation comes in. From negative infinity up to 0, we're decreasing. From 0 to positive infinity, we're increasing. When functions are familiar, or when you have a graph handy, it's going to be easy to determine those intervals, or easier. But not all functions are familiar to us, and so we need a plan for trying to locate these intervals. And the strategy is outlined here in this slide. Basically, we're going to find all the values of x where the derivative is equal to 0, or where it's discontinuous, meaning where f prime is undefined. And then we're going to look at the open intervals between those points. That's what it means by open intervals determined by these numbers. Then in each interval, we're going to select a point which we call C, and we're going to plug it into the derivative and find out if it's positive or negative. All we have to check is one point because we've already looked for the zeros. So once we pick one point in that interval, if it's positive, we're going to say that it's increasing. And then if we plug it in and the first derivative is negative, we're going to say it's decreasing. I think it'll help if I show you an example. So our strategy for locating those intervals, which we call monotonic intervals, by the way, is to start by taking the derivative of the function. Here we have this function f of x equals x cubed minus 3x squared minus 24x plus 32. And I think you'll agree that the derivative, using the power rule, is 3x squared minus 6x minus 24. And first thing we need to do is locate those zeros, or places where this thing's undefined. Well, this is a polynomial, a quadratic trinomial, and it's defined for every value of x, so there's no place where it's undefined. But we do have zeros, so we need to locate those zeros. And to do that, we're going to factor this thing. So we got to go back to our old factoring method, I'm going to kind of use the guess and check method because there's only one way to get 3x squared. And then 24, let's see, 6 and 4. If I multiply by 4 here and 6 here and make this negative and this positive, I think that does it. Yes, it does. And so from here I can get my zeros. If I set this equal to 0, there's two places where it equals 0. The first one is negative 2. That's from the first factor. And then the second one is positive 4. So we've located these zeros, and then we can determine our intervals. And here's how you do it. You make what we call a sign diagram. So basically with a sign diagram, we draw a number line, but we don't have to put all the numbers, just our two numbers that we found there. So I'm going to put negative 2 here, and then I'm going to put 4 here, and then keep that going. And what we're going to do is pick a C value in each of these intervals. So I need a number between negative infinity and negative 2, a number between 2 and negative 2 and 4, and then a number bigger than 4. And we're going to plug each of those into the first derivative. So for example, I'm going to pick negative 3 to be over here, and I'm going to plug negative 3 into the first derivative. I think you'll agree that that works out to be, negative 9 plus 6 is negative 3 times negative 7. That's going to be negative 21. So that is a negative answer. All we need to know is the sign of the answer. And then we put a bunch of negative signs here. And I also like to draw an arrow telling me that that function is decreasing on that interval. In the middle, I'm going to pick my favorite number to do math with. That's 0. I'm going to plug that in, f prime of 0. You plug zeros in here, you get, I think I made a mistake. Yeah, I'm a dingling. I could restart this, but why don't I just start over by erasing this? I did make a mistake. Negative 3 times negative 7 is positive 21. This is a positive interval, and that thing is increasing. When I plug in 0, I get negative 24. That's a negative interval, so this thing's decreasing. The really disappointing part about this is I'm looking right at my notes, and sure enough, I just ignored them for a minute and made that mistake. And then over here, I'm going to plug in 5. If you plug in 5, you get 21 times 1, which is positive 21, so this is a positive answer. And that tells us this thing is increasing. Okay, because I messed that up, let me just go through it again. We use the first derivative to find these points, which we're going to end up calling critical points. It's places where the derivative is 0 or undefined. Once we find those, we use that to divide up our number line into chunks, these intervals. And we have 3 chunks because we have 2 points. In this first interval, you pick a number. I picked negative 3. I found out that the first derivative is positive. It's got to be positive everywhere over there. So I mark that. I plug in 0. I find out in the middle chunk is negative, so it's negative everywhere. That's decreasing. And then I plug in 5. I get a positive 21. I find out that's positive, and I plug that in. And so I am increasing on 2 intervals. Negative infinity to negative 2 and 4 to positive infinity. And then I'm going to squeeze this in here. I'm decreasing on negative 2 to 4. All right, that's decreasing. And we can verify this with a graph, which I'll show on the next slide. Thanks for your patience on this problem, by the way. Okay, so here's how this translates to the graph. We found the point negative 2 was what we call a critical point, or a place where the derivative was 0. We also found 4 where it was also 0. And you'll notice that the function was increasing after I correct my mistake everywhere from negative infinity all the way up to negative 2 on the x-axis. It's decreasing in this range, right, because it's heading down. And then over here, from 4 to infinity, it's increasing again. And that's what we found using our strategy, but we can find it on the graph as well. So I'm going to try it again with another example, and we'll see if I can do this without making any mistakes, especially since I'm looking right at my notes. Okay, so we're supposed to take the first derivative, and we're going to use our power rule. It still works with fractional exponents. The derivative is going to be 2/3 x to the negative 1/3. Now that's not very practical to work with, so I'm going to convert that to radical notation. Since it's a negative power, that term is going to go to the denominator, and it's a 1/3, so that's a cube root. So this derivative function is actually 2/3 cube root of x. And I'm going to tell you a little secret about rational functions here. The only way that a rational function, a fraction, can equal 0 is if the top number is 0. And 2 will never be 0. So this derivative is never going to equal 0. However, we do have a critical point when x equals 0, because that'll make this fraction undefined. So our critical point that we want to keep an eye on is x equals 0. We're going to use 0 to divide the number line up into two pieces. And all I have to do is check a number over here, and I'm going to check -1, so I got to plug -1 into the derivative. When you plug negative in, the cube root of -1 is -1, so this is -2/3, so this interval is negative, meaning this guy's decreasing. Over here I'm going to plug a 1 in, and 1 is like my second favorite number to do math with. F prime of 1, you plug a 1 in here, you take the cube root, and you get 1. That means this is 2/3. 2/3 is positive. So the sign diagram over here is positive. That means this thing's increasing. And so let me see if I can write this a little better. I'm decreasing on negative infinity to 0, and I'm increasing on 0 to positive infinity. Let's take a look at the graph. So here's that function x to the 2/3, and you'll see this thing is decreasing on the left-hand side all the way up to 0, and it is increasing on the right-hand side from 0 to infinity. So we were correct. From negative infinity up to 0, the function is decreasing. From 0 to infinity, the function's increasing. That was a little bit better. Let's try one more. Okay, so here we have an interesting function, x plus 1 over x. And in terms of taking the derivative, remember it's probably easier to write this with a negative exponent so that I can use the power rule. So let's do that. F prime of x is going to be 1. Let me put an equal sign in there first. Come on, man. It's going to be 1. And then the derivative of negative x to the negative 1 is negative x to the negative 2. So that's going to be minus, I'll put 1 over x squared. Write it with positive exponent. And then our job is to find out where this thing is 0 or where it's undefined. And it can equal 0 in two places. If I put a 1 or a -1 in for x, I get 1 minus 1, which is 0. So two of those important points, those critical points, are -1 and 1. But then we also have an issue at x equals 0 because the value of 1 over 0 is undefined. So we're going to chop our number line into 4 pieces this time. Let me draw this over here. So we go from -1 to 0 to 1 and then onward. And that means I got to pick 4 special points to test. Well, I'm going to have to choose one over here. I'm going to choose -2, so I'm going to plug -2 into f prime, meaning I'm going to put it right over here. When you square that, you get 1/4, so 1 minus 1/4 is 3/4. This is positive. In here, I'm going to have to pick a fraction. I'm going to pick 0.5, and I'm going to plug that in. And when you do that, you're going to get 1 over 1/4, which is really a 4. So that's 1 minus 4 is -3. So this thing is negative. So I'm increasing here, I'm decreasing here. On this side, I plug in, this is a negative 0.5 by the way. Over here I'm going to plug in positive 0.5. The same value happens because when you square it, it turned it positive anyway. So this is also decreasing. And then finally, I'm going to pick 2? Yeah, I got to pick a number over here, so I'm going to pick 2. And when you plug 2 in here, you get a positive value again, 3/4. So this is an interesting function because it's increasing, then it's decreasing, then it's decreasing again, then it's increasing. But one thing you need to remember is that this thing was undefined at 0, so there's a vertical asymptote there. So let's take a look at this picture and see if our analysis matches the graph. And here's a picture of the graph of f of x, x plus 1 over x. And again, we had it right. Here's -1, even though you can't see it on the x-axis. And that's the place where it changes from increasing to decreasing. So from negative infinity all the way up to -1, we are increasing for all these numbers. But then notice in here, we're decreasing just between -1 and 0. Then there's that asymptote I talked about, and the function continues to decrease, but from the top of the number line instead of the bottom. So in here between 0 and 1, we're still decreasing. And then finally from 1 all the way to infinity, the function's increasing again. Now when you write these intervals, you got to be careful because we can't count 0. So we would say increasing, let me write this over here. We're increasing in 2 places, from negative infinity to -1, and from 1 to infinity. And then we're decreasing on 2 intervals also. We can't say just from -1 to 1 because 0 is undefined. So we have to go -1 up to, but not including 0. And then 0 up to 1. So that's how you're going to write that. So this was an introduction to finding these intervals where the functions are increasing and decreasing. We're also going to talk about finding extreme values in the next video. Good luck.